William, do you have any objections to the videotape and posted online?
No, that's okay.
Sure. In that case, it's my pleasure to introduce William Simmons, who is going to talk about differential algebra sampler.
Okay. So, it's a pleasure to be here. Thanks for the invitation, and it's good to be back at the Colchin seminar. So I'm going to be talking about a topic that I actually talked about when I was here as a graduate student, and I've learned a few things since then. And so most of these, the actual results, well, Dave will be familiar with, but there are a couple of new directions, and have thought, continue thinking about this problem, sometimes just in the back of my mind, but continue thinking about this problem. And I think there's some interesting things to be said that hopefully, hopefully you'll find interesting. So just to get started, in general, if don't say anything otherwise, we're going to be working over differentially closed fields, use MathCal F here. And most of what I'm going to say generalizes to the partial case, but for the examples that I'm going to be using, I worked them out over the in the ordinary case, just a single derivation. And in particular, James Freitag has looked at this in the partial case, and general base tools that I'll be referring to all seem to transfer over basically without change. There's some issues because dimension is more complicated in the partial case, but other than that, it doesn't seem to have a big impact on the question. And because the main thing that I want to talk about, namely complete differential varieties, it's still there's still so much difficulty in actually identifying when a variety has this property and when it doesn't, that hopefully there's not too much loss of generality in just sticking to the ordinary case. But I will make some comments about that as we go along. So we're going to be looking at closed sets in projective space. So this is kind of a natural setting if you want to have the property of completeness, which I'll recall in just a moment. So like in the algebraic case, if you have varieties in projective space, they have to actually be projected, defined by homogeneous polynomials in order to have a chance of satisfying this property. So we have this monster model U, big differential field in the background, but I don't think it really shows up again. And just the easiest example of a differentially homogeneous polynomial. This is what you get when you homogenize the equation x prime equals 0. So these solution sets are projective differential algebraic varieties, which is kind of a mouthful. So probably just say projective differential varieties or differential varieties, or even just varieties, if it's clear. So if it's not, feel free to clarify. And one point that our first example is going to show is that projective closure is tricky. And as in the algebraic case, even when you have a presentation, if it's not appropriately large, that when you homogenize, you can get a set of defining equations that's strictly larger than the projective closure. And this looks really weird in the case of differential varieties, because we'll see an example where you can homogenize and you add a point, but it's not really. So in P1 in the projective line, you add a point, and it's not actually in the projective closure. So we'll go through the proof of that, which is unintuitive, but there's kind of anomalies abound in this area. So the main definition that we'll be discussing is that of completeness. It's an analog of compactness. It's used more in if you had a Hausdorff space, but this is algebraically nicer. So dealing with the projective differential variety V it's differentially complete, or often just say complete, because that's the notion interested in for our discussion. It's complete if when you take any other projective differential variety and you take a closed set of the product, then the projection into the second factor takes closed sets to closed sets, so defined by differential polynomials. And closedness is a local property, and so we can assume that the second factor is, say, affine space if we need to. So that could be convenient when necessary, but and in fact that's what I'll usually assume. So a lot of the properties carry over just without change. The proofs don't have anything to do with the fact that you have a derivation or derivations floating around, but there are a couple of big ones. And the first one, both looked at by students of Dave, is that complete differential varieties have to be small in some sense. So it must have differential dimension 0, where the usual differential transcendence degrees is what I'm referring to here. This carries over as well to the partial case that James Freitag confirmed that the arguments basically go through without change. And in the ordinary case, then this differential dimension 0 corresponds to having finite rank in any of your usual model theoretic ranks. That's not quite true in the partial case, and so there's a gap there in terms of we don't know if there are any examples of complete differential varieties that have infinite, say, Laskar rank, but that still have differential dimension 0. So that would be, for instance, if you had m commuting derivations, then you could have Laskar rank strictly less than omega to the m, and there's a gap in there, and so that's. But in any case, they still have to be small in some sense to have this. And so since I'm generally sticking to the ordinary case, I'll kind of indiscriminately mix finite rank, zero-dimensional terminology. So again, if it's not clear, just ask for clarification. So complete differential varieties have to be small, and this is related to the second irregularity that shows up with this notion, namely that one of the prized properties of complete algebraic varieties is, namely, say, for instance, if you're just sticking in projective space, projective varieties, is that there aren't very many maps from them into affine space. So if you have a projective algebraic variety, then there's only constant maps into affine space. But that's not the case here. And basically, just think about it as the reason being that these things are so small that they can actually fit in single affine chart. And so the map to itself is a non-constant morphism of differential morphism. So you do lose that property, and that's often what's used in applications, but not entirely. So it's still worthwhile looking at this notion. But if you could do something about that, then that would be desirable, because, for instance, in the algebraic case, that second property is often what you would want for doing things like showing that projective algebraic groups are commutative, so abelian varieties. But so in any case, it's like I say, it's still a useful property. So I want to go over a list of known complete differential varieties. Say a little bit more about what's not on here, but in general, so what I have here is a few general classes and kind of some grab bags that just amount to cases that I was able to identify. And you'll kind of see when we talk about the method for finding the, for confirming completeness, why it looks maybe a little scattershot. It's basically kind of found the method and then try to apply it to whatever is at hand. And well, certainly are other examples around that you could verify with this method, but we'll see why the situation is complicated, and so might not be the most interesting thing to just get a bigger and bigger list of complete, because there are some incomplete examples, and that's we'll talk about as well. So first of all, linear differential varieties. So if anything is going to be complete here, then these should, and they in fact are. Confirm this when you have just a single variable, and just backtracking. So I did mention that everything has to be projective. So you should think about if we're talking about a single differential indeterminate, we're talking about subvarieties of P1 here in general. If you have a linear differential equation in a single variable, then their projective closures are all complete. Believe that the same thing would hold in several variables and also in the partial case, but I haven't confirmed that. It's messier to do that, but I've thought a little bit about that. If there's any justice in the situation, then that should be the case as well. Here's one of these sporadic examples here. Another, if you just have non-differential polynomials with just a single variable, the nth derivative of x, coefficients in your field, their projective closures are also complete. So.
Ask a question
Sure.
about this. In the classical algebraic setting, one of the uses of this is that there are no non-constant global functions.
Exactly.
So, on a projective variety.
Mm-hmm.
So, can you say anything about the functions in this projective setting and differential-wise?
Well, so I guess the main thing that I could say about that is just simply that these things live kind of a dual life, that they can be projective but contained in a single affine chart. And so really anything that happens with affine varieties, and so we'll talk about some concrete examples, but can happen with these. So if you've got, so you can have a large
it doesn't
mm-hmm.
limit functions in any
right, as far as, mm-hmm. which is kind of unfortunate, but it just comes back down to the fact that relative to the ambient space, these things are small.
And here, when you say functions, you mean differential functions.
Right, differential morphisms. So
if you were to restrict to algebraic things, would you still have non-constants? I guess if it's in a single affine chart.
Right, I mean the identity map would be so. Yeah. So I mean I thought a little bit about that, but at least so far I haven't seen anything really interesting that you could say about kind of the functions defined on these varieties. So in the first order case, this is a generalization, at least if you're restricting to a single variable, of the first known examples of complete differential varieties. Namely, Kolchin showed that if the constant points, so all the points that can be written with all the coordinates having derivative 0, that those form a complete differential variety. And so at least, again, with a single variable, that's an equation of this form with p being 0 and q being 1. Wai-Yan Peng showed that if q is equal to 1, then the projective closure of the equation x prime equals non-differential polynomial. in a single variable, that is also complete. And so it is the case, and it's trickier to show, but was able to show that if Q is just any polynomial non-differential in X, then the same thing holds there. And another sporadic example that's there pretty much because of the principle that if all you have is a hammer, everything looks like a nail, and so just found this nail was sticking out. Mm-hmm.
Question. So you're saying that if you just look at the equation x prime equals 0, so they're just the constants,
Mm-hmm.
you're saying that that's complete?
The projective closure. So in
So
right.
the projective closure of that is actually P1.
right, because in that case so you homogenize, you get that homogeneous equation that we saw at the beginning, and the point at infinity 1, 0 satisfies that.
So in all these cases, you're talking about the projective closure.
Exactly, right. So yes, it's not true if you don't have projective closure, but right, just mm-hmm. Right. So there's if you go higher order, so other than the linears, I do know of this example, and we'll sketch its proof a little later on. But the projective closure of this differential variety, which is interesting, it's Poisson used it as an example. It has Morley rank 1, but it's a second order differential equation.
So I suppose you also have examples of equations whose projective closure is not differentially projective?
So the algebraic projective closure, you mean?
Well,
Or-
whatever projective closure you're talking about here.
So, okay, so say that one more time. That
So for the past slide and a half, you were saying if I take this equation
and say the
then
projective
take the
closure, then that is
then
complete.
that is differentially projective.
Yes,
So the projective closure is
Differentially complete. Right,
So there, the projective closure is this differential projective closure. So
Mhm.
are there examples where you take equations, take the differential projective closure, and it turns out to not be differentially complete?
Yes, So in fact, that's the prime bad example that we're going to show. So
Okay.
the first bad one on the list is one where the projective closure behaves anomalously that is not complete. So this guy is, and the method that we'll talk about. I guess the reason why there are fewer higher order equations is that it just gets really, really messy to work out by hand or even with computer. But there are some that will work. And then just kind of closing up the class here, like I mentioned, most of the formal algebraic properties of completeness holds when you go over to the differential case. And so if you take subvarieties, projective subvarieties of complete varieties, they're complete. Images under morphisms, if you have a complete domain, then the image is complete. And products. So you can combine, mix and match these preceding examples. But up to the fact that, well, constants, it's true for in the partial case as well, and the fact that for these, if you let Q equal 1, then the analog in the partial case, James Freitag confirmed basically the same arguments as Pong, that holds, but those are all the complete varieties, differential varieties that I know of. So I thought for a long time that that perhaps everything that was finite rank and projective would be complete. I'm going to start by looking at I guess the smallest, the simplest example that I know where that's not the case. But first, I want to discuss its projective closure and the arguments showing that its projective closure behaves anomalously seems closely tied up to this issue of completeness. And in any case, it's interesting regardless. So wanted to look at that proof. So again, so we're working in P1, and look at the equation x double prime equals x squared, not homogeneous, but if you homogenize it, you do get something that is satisfied by the point at infinity. So it's a little bit ugly. We'll see what the equation is in a moment here, but it's strange because you just add a single point. When you homogenize, it should be in the closure, but we can show that it's not. That in fact the original affine variety is a proper projectively closed subset of the locus here.
Delta H means delta what?
Delta homogenized, the delta homogenization.
Oh, delta homogenized.
Right. So convenient to write it out in this form that claim that the projective closure is this set V. And so we're kind of going to go up, homogenize, and then cut out the point y equals 0, this second variable. So that's just another way of writing the restriction to the first affine chart. The basic idea then is to just show that the intersection of V with each of the two standard affine charts of P1 is closed in the affine Closure topology there. So just general topological fact, doesn't have anything to do with algebraic geometry, that if you have a subset and an open cover, the intersection is closed in the subspace topology on each of those open sets, then the whole thing is a closed set of the overall space. So just need to check that the restrictions is closed in each case. So the first one, well, that's obvious. It's defined by the x double prime equals x squared. Now the second, so this is what you get with the when you homogenize and then let x the first coordinate equal 1, and but you also have this stipulation then that y prime is not equal to 0. So we have an inequation. It's not obviously a closed constructible set. So we have to do a little work to show that that is the case. So just like we're working over a differentially closed field, and so the it works just the same as in the over algebraically closed fields, that if you have a projection and you look at the elimination ideal of all polynomials that vanish on the variety that don't contain the variable that you've eliminated, that defines the closure of the projection. So if we're just going to show that the closure of the projection is actually the image of the projection. And you can see that the image of these two equations then is exactly that system up top. Okay, so how do we know that that it defines exactly the image? Well, so it's the issue of whether or not y kills off everything in the elimination ideal or not. And so just need to find a differential polynomial that doesn't vanish at 0, or in other words, has a non-constant term. So here non-constant just meaning not equal to 0, not necessarily that its derivative is 0. So there is software, for instance, in Maple, that for differential algebra, the differential algebra package, I believe it's been incorporated in Sage, and so it's becoming more widely accessible. But at least for small examples, it's probably easiest to either work by hand or just differentiate a few times and use standard algebraic computer algebra packages to look at the algebraic elimination ideal. So turns out if you differentiate this guy once and then look at the the algebraic elimination ideal, so treating each derivative as a separate algebraic indeterminate, and see what comes out, then find out that this polynomial is in the elimination ideal, which is what we needed because of this -1 that's sitting there. So you may or may not like that. So if you don't happen to trust Maple, then you can check by hand that we have the following equation. So this P1 is the polynomial found up in the second bullet point, and then P2 is the equation in question, the dehomogenization to the second chart, and then P3 is its derivative. And so this isn't showing directly that that P1 is actually in the ideal, but what it is showing is that the locus of the variety of, so the zero locus of P1, P2, and P3 is exactly the image. And so that is a closed set containing the image, or in other words, it is the image. So however you like it, we've shown that that this restriction to the second chart is in fact differentially closed. So I guess the reason then is it's like I said, that geometrically this equation right here shows that the image is exactly the set of solutions of P1, P2, and P3 all vanishing. But I suppose it should also be that you could argue that it's a prime differential ideal, and so and y doesn't end up being in there.
So how do you know that?
Well, I guess I know that because just geometrically that I showed that the solution set is exactly. Maybe I should write it down.
So it seems to me that what this equation shows is that y times p1 is in the differential ideal.
Right.
And so if you know that the differential ideal is prime,
right,
then either y is in it, which is clearly false, or p1 is in it, which is what you wanted.
Right. And so right.
So how do you know that it's prime?
That's right.
So I don't actually need to show that. So I just need to show that. Is this sorry? Going off camera there. Show that the solution set negative y double prime plus 2y prime squared minus y equals 0, and y is not equal to 0 is equivalent to negative y double prime plus 2y prime squared minus y equals 0, and this other. So right. So maybe we won't write all of it out. Minus 1 dot 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 equals 0. And so
you showed that.
right. And so that's what given that this equation is true, then let's see. There's two containments. If this is true, then certainly y isn't equal to 0 because of this negative 1. So it's contained in there. But if that is the case, then because of this equation, since y doesn't equal 0, then P1 must be 0. So, right. So yeah, it looks strange, and it's that's how it goes, and maybe it has something to do with the fact that it actually isn't complete. It's title of this slide, A/the bad example, because this particular family is the only family that I know, And so it seems to be both difficult to show that it seems difficult to identify completeness in general, to actually show that it's, an example is complete or that it's not complete for reasons that we'll discuss. So this particular family, x double prime equals nth derivative, where n is anywhere greater than or equal to 2, claim that they're all projectively closed. And so ordinary, of course, they have finite rank, but they're not complete.
But do you really mean the nth derivative on the right-hand side? Because then it's a linear equation, and you said that linear ones are always linear.
N greater than or the projective closure. Oh, I meant the power. I'm sorry. That's that is a typo.
It's the projective closure.
Yes, right. Projective closure, and then scratch the parentheses, and you're right.
But I don't know.
Right.
I have a low power.
So, talk about the sketch. So just projectively closed. The case that n equals 2 is what we just saw, and for n greater than or equal to 3, you homogenize and plug in the point at infinity, and it just doesn't satisfy it. So those nothing tricky to do there to show that it's already one of these strange affine projectives. So we have to come up with an appropriate counterexample. So this is the closed set in the product that we're going to project and find non-closed image. So in this case defined, so y is the variable corresponding to the second factor, and think about y times 2x to the n plus 1 minus n plus 1 x prime squared equals 1. And the image is going to be the set of constants less the 0. And this is a problem because the constants are an irreducible Colchin closed set, and throw out 0, then is no longer Colchin closed. So one direction, we take a point in the image, and so there exists some x satisfying these equations, and differentiate this the second equation that we had. We have the relation x to the n is equal to x double prime. So because of the I guess kind of S polynomial-like way that we chose the coefficients and exponents there, the second summand vanishes, and we're left with this y prime times 2xn plus 1 minus n plus 1 times x prime squared equals 0. So again, from that first relation, that second factor is not equal to 0, so y prime must be 0. And clearly it's not 0 because of that special 1. So it is contained in the constants and not equal to 0 is what the image is. For the other direction, then here's where we're going to have to use the fact that we're working over a differentially closed field. So suppose that we have a non-zero constant, and we need to find an x satisfying the definition of our proposed non-complete variety, and then satisfying the second part. Well, the axioms of differentially closed field tell us that so the second equation, that first order, there exists a solution that also doesn't lie on a variety of smaller orders. So we can specify both this equation and this inequation there. And the nice thing about that choice then is that it tells us that x prime is not equal to 0 without having to spend a non-positive formula saying that x prime is equal to 0. So if we differentiate, then we can divide out the x prime because of that kind of back sneaky way of ensuring that x prime is not equal to 0. And dividing out, we get that x double prime satisfies this relation. So it is in the image. So that's a problem. We've got not only, so yes, the one obvious obstacle that Pong already told us about was that you can't have positive differential dimension and be complete. And well, that would be okay. You might think that there's a close connection between finite rank differential varieties and algebraic varieties. So the nicest possible thing with that would be to say, oh, it's just the extra express. Sorry, was.
I don't. Go ahead.
Okay. Yeah.
I don't agree with that general philosophy.
Okay. We'll get that just a second here.
Wildly different.
Okay. Okay, I guess this at least maybe was kind of my thinking looking at it originally, and kind of why I expected that that might be the case. But as we see, that it's not. In fact, it's really not true, and but in fact, there is more going on here. So, I should say something about why that is the case. So there's actually an example. So the original example showing that projective space, differential projective space, is not complete is due to Colchin. Pong wrote up some explicit equations, easier for graduate students to read, that explain this. And it has similar features. So this is what Pong's example looked like. And the argument runs parallel to what we just described. However, that wasn't actually the way that I determined that this family of bad examples existed. And well, I guess for a couple of reasons. First of all, I wasn't really looking for it because everything else seemed to have worked out. Just seemed to be a matter of trying hard enough to establish completeness for finite rank differential varieties. And this extra constraint makes things harder. It's more ticklish to be able to find an example like that. If you modify the example of Pong, you can tweak the coefficients, for instance, and the degrees, and it doesn't really change how the proof works. In this case, we're using something very special here. So, for instance, if you let n equal 3, then we're relying on cancellations that happen like this. And if you change the coefficients just a little bit, then this is actually the image is still closed. And so something about having this extra relation in the finite rank case there makes it harder, apparently, to find counterexamples. And so that may be one reason why I didn't just assume entirely that that everything finite rank and projective would be complete, but just never got anywhere initially trying to think about counterexamples, and this might explain why that it's harder to find counterexamples when you have extra constraints imposed. So how I guess would encapsulate all that is that not only is having too few relations, so like in this first example, there's no restrictions on x at all. And so that leaves you room to kind of cook up an example like this. But even if you have enough relations to cut you down to 0 dimension, that if they're just of the right kind of like this anti-derivative type situation where the derivative ends up being in the ideal, but the original isn't, then you can have specialized bad examples witnessing incompleteness. So I think that's probably enough negativity for the moment. I want to talk about some positive results and explain also where that list came from before, and talk about some generalizations of the method that I found since I was last here. And just to review that, wanted to remind you of a observation due to Van den Dries. So this is basically positive quantifier elimination result. Analogous to the well-known criterion for quantifier elimination, but if you expand the set of maps under which you want your first-order formula to be preserved in going from one model of the theory to the other, so to homomorphisms, in this case mean weak homomorphisms, so just if we had relations in our language, then we just need them preserved in the forward direction. Then you can eliminate the quantifier, and that there's an equivalent formula without negations for defining it. So of course this is what we're interested in here, because we're interested in sets defined by polynomial equations. So at least in terms of this topic, the most interesting part of Van den Dries' note where he talked about this was he gave a really slick proof of the fundamental theorem of elimination theory. So namely that projective algebraic varieties are complete. And we'll see the ingredients. Everything works exactly the same in the differential case, except this first part. So this place extension theorem refers to the fact that if you have a ring homomorphism on a subring of a field, and you extend that maximally to as far as you can so that the domain is still contained in the original field, then you get a valuation ring of that field. And having a valuation and the fact that you're projective, so that you can divide out by you can multiply by non-zero constants, and your representative is gonna solve the system if and only if the original one did. Basically, all you have to do then is, if you have so I'm being a little bit sketchy here because we're going to go over the same argument in more detail in the differential case. But just to say what's different here about from the algebraic to the differential case is that you actually do have a valuation. So if you divide, you take a representative. So you have your projection where your first factor is projective. You have a representative point there. Divide by the element of least value under the valuation, then you'll show that point actually there's a representative of this point in projective space that actually has all of its entries in the valuation ring. And since homomorphisms preserve positive formulas, then as long as you have all of your parameters in the domain of this homomorphism, then the formula is preserved. So that's kind of the quick sketchy way of saying what Van den Dries' proof works like here. But suffice it to say that the main ingredient is that you can extend homomorphisms on subrings to homomorphisms on a valuation ring. And then also the fact that if you work with an algebraically closed field, that those are existentially closed, that comes in. But that's really all that's going on here. So the main novelty when you look at the differential case is that you no longer have valuation rings. If you did, had the same construction generally gave you a valuation ring, then the same proof as Vanadries would go through, and you wouldn't have the bad examples that we just talked about. So that's how I know that these things aren't generally valuation rings. The essential definition is, well, if you don't have a valuation ring, what do you have when you extend a differential homomorphism to a maximal subdomain of the field? Well, you get something that we call the maximal delta ring, Ritz and Bloom knew that this was a local differential ring, and then the key factor for, at least for our purposes, is that having this local differential ring implies that you have an element of your differential field that's not in this maximal differential ring, if and only if you have units in the differential polynomial ring generated by with coefficients from the maximal ideal and this element.
Still parsing your definition, it seems like whether or not R is a maximal delta ring depends on the homomorphism P.
It does. Mm-hmm.
So it's a maximal ring with respect to P.
Right. So in the proofs we will we assume that there is some such when we reference a maximal differential ring, it's with respect to some homomorphism, but the only thing that matters there is that this maximal differential ideal is the kernel of that homomorphism.
So you're saying that this magically becomes independent of P because being a unique maximal differential ideal, that doesn't seem to say anything about P.
So right, I mean, not in practice. So it's we use this very formally. It's in fact to show that there's a version of this method that just depends purely algebraically on differential ideals. So we can eliminate reference to these maximal differential rings through just a little bit of model theory and so right. So I mean, it's very So I can't show you a really good example of such a ring that they exist by Zorn's lemma, and the only thing that ever really used is that they are local differential rings with this property.
And M curly X is what?
So just differential polynomials with coefficients in the maximal ideal. Mm-hmm. So another fact that will come into play that is useful for looking at these sorts of examples is that these maximal delta rings are integrally closed. And Morrison also showed that if you have an element of this delta field K over this maximal differential ring, and if it satisfies a linear differential equation, and its reciprocal is not in the ring, then it itself is. And so that's basically the algebraic version of the proof that, so this basically, in algebraic terms, this is what completeness of linear differential varieties amounts to. So I was surprised to see kind of gift wrapped in her paper there. It wasn't not stated geometrically at all, but well, I'll show you rather than telling you. So because we don't have valuation rings in general here, what we have is a criterion or a condition under which, or an equivalence condition for completeness, rather than a theorem saying that all projective differential varieties, whether finite rank or not, are complete. So Pong stated this for affine varieties and showed that the variety is complete if and only if, when you have a model of a differentially closed field and you have a maximal delta ring, that the k points of your variety are exactly descend to points in this maximal differential ring.
Does that require the base field to be differentially closed?
So differentially closedness. So in verifying, where that hypothesis comes in is in using the positive elimination results of Van den Dries. So what you do is you start off to show that you're equivalent to a system of differential polynomial equations. You need to show that the existential defining the projection, that formula is preserved under homomorphism from one model of your field to the other. And so what you want to do then is that it might not be a maximal homomorphism, so you want to extend to a possibly larger subdomain of your field. I should draw that. So we have a model here. You've got your subring there, and over to some other model. Well, if this, we were calling it phi, the homomorphism, if this is not maximal, you may have to extend to some a tilde with codomain some larger field L, and then since you want to be able to push it back down, then that's where differential closedness is. You can assume that whatever this is, well, if it's not differentially closed, it embeds in a larger one. You show that the projection, that the statement made by the projection is true, that there exists something in V cross AM down to AM. So it exists up here, and then you can pull it down there. That's where the use comes in there, to satisfy the requirements of that positive quantifier elimination.
Trying to get some intuition for what these delta maximal, what these maximal delta, k maximal delta rings are.
Mm-hmm.
If R is a k maximal delta ring,
Mm-hmm.
how far is k from the field of fractions of R?
That's what I was going to ask about.
So the I guess so if it were just the field of fractions, I mean, we know by Morrison that it's integrally closed. So it's that.
Oh wait, R is integrally closed in K?
Yeah. So
Is that always true? Yeah.
Right.
Yes.
The K maximal delta rings are integrally closed.
But yeah. So what if the field is the differential closure of Q? A differential closure. Can you find one of those maximal delta rings whose field of quotients is the differential closure of Q? Do you know that?
I don't know that. In fact, so that, I mean, this is I mean, it's it's something that so I guess the basic answer is that I don't know much of anything about it, about particular forms of these things.
Yeah.
The results that I know of are kind of this form, and that I don't have any explicit examples.
What if you don't insist that field is differentially closed?
that so the definition isn't required, so it makes sense. But the criterion or the condition for completeness seems to require the closeness, differential closeness.
If I'm a subring of a field, and I'm integrally closed in that field, how am I not a field? For every Bob in me. Oh, I'm being stupid. Sorry. Sorry.
That's fine.
Sorry, never mind.
Right. Yeah, they're kind of hard to get your hands on.
Yeah, if you don't.
Okay, so that brings back the question of what is the field of fractions?
So I mean that again, I guess that's something that I haven't really considered, because it's only been the formal properties, and in fact I can show that we don't need to just mention them at all, these maximal rings at all, to get a condition for completeness. So, but I mean that would be certainly something that, I mean, like Pong told me, I mean, somehow the major issue here is trying to understand what differential integral closure should mean. What and there are various non-equivalent definitions in the literature, and this is kind of a halfway house, or it's a stand-in for what you'd really like to have, but that's kind of the extent of what I can say about them.
They're not usually differential rings. So you can't just grab one and say.
So that is Pong's criterion for affine differential varieties, and in some sense that's all that you need, because these things are small and you can actually embed them in the affine line if you've got a complete differential variety. But still, if you want to understand what the extent of this notion is, because when I started looking at this, didn't know whether there were any kind of non-trivial incomplete examples.
You mean that for any delta variety in A upper n can be put into A upper 1?
Yes, so you can do a series of projections, you can get it into A1, and because it's finite rank, then it will
well, it has to be small anyway.
Yeah,
right.
The term of constants projects embeds in the line. The equation goes up to 6th order. So you always have to get complexity when you simplify. It comes into work.
Yeah. So, so in some sense that gives kind of the best result that you can get trying to imitate Van Andrea's proof of the fundamental theorem in the differential case. But if you're trying to look at concrete examples, and especially since it can be hard to recognize whether or not a variety is projective, we saw that with x double prime. You would have x double prime equals x squared. You would have thought that that's not projective, but it actually is as an affine variety. It's the locus of some intersection of it's a projective variety already. So we would like to not have to go through that step, verify, determine what exactly is projective or not. We just like to say, we'd work with projective varieties, look at the different charts, and do that. And so that's one motivation there. And one other thing that that makes maybe this theorem here at the top not the end of the story is that when you try to verify the valuative criterion, and say some more about what that means in just a moment. But it turns out that you feel like you're just working algorithmically, that it's kind of an elimination argument, and there's nothing. You're not really using anything too special about these these maximal differential rings. So the basic procedure then is say, well, if you have a variety that you think is complete, suppose that it's not, and then that must mean that there is some k-maximal delta ring for some homomorphism phi there, where you've got a bad point, that you've got a point, k point that is not